Hi, my name is Vineet Ratish, and today I will be presenting on the HDL implementation of Lenet interface engine for the MNIST digit recognition. So this is the table of content for us. This is what we will go through in the presentation. So let's start with the introduction. So our tasks involve implementing the forward data path of the Lenet model in hardware using Xilinx Vivado or Vitis HLS, and this consists of three main parts, which is the Lenet architecture, the half precision floating point, which refers to the 16-bit floating point arithmetic for multiplying accumulator operations, also known as the MAC operations. And using half precision reduces the hardware resources usage and power consumption while maintaining accuracy for many machine learning tasks. So we could have used a 16-bit floating point arithmetic, but that would have had more resource utilization. And we have the bit accurate half precision max, uh, which the use of the previously developed FP16 max in our previous projects. So finally, we developed the hardware descriptions for the Lenet forward part using Verilog. So what is Lenet? The Lenet interface engine is a computational tool for performing predictions using the Lenet architecture and an early convolution, an early CNN, which is a convolution neural network, which I'll be explaining in the next slide. So the Lenet architecture, as you can see in the diagram below, consists of the convolutional layers, the subsampling or the pooling layers, and the fully connected layers, which are the final classification. Now, as you can see, this is the layout of a typical CNN in the left image. So we have the inputs, and we have add the weights and biases, and we perform convolution, and which is followed by pooling, and we finally get the output on our output ports. And to the right, you can see is another diagram of a CNN in which includes the input, the hidden layers, the final output, and the final output layer and the final output which we obtain. Now, to obtain the data set for the images, we have used the MNIST, which is the National Institute of Standards and Technology database, and which is a widely used data set in machine learning models and computer vision for training and evaluating models. And we use the handwritten digit recognition data set for this. Now, in CNN, we also have the activation function. So there are multiple activation functions, such as the sigmoid activation function and the ReLU activation function. And we have used the ReLU activation function, for which uh, as you can see, the graph, it has zero for all values below zero, and it has a linear slope for values above zero. And the equation for it is f of x equal to max of 0 comma x. Now I will explain the code for our project. So we have three main parts, which is the lanet.cpp, the lanet.h, and the test.cpp. So the lanet.cpp involves map functions which perform the multiply and accumulate operation, which is a key to neural networks. And next includes the convolution and the pooling layers, which applies filters to extract features from input data, while the max pool function reduces the spatial dimension by selecting the maximum value in pooling regions. The next part is the fully connected layer where we add all the weights and biases and apply the activation function. We have a we have a soft max function which converts the final outputs into probabilities, and we over here, and we have the forward pass with which orchestrates the data flow through convolution pooling and the fully connected layers, culminating in the soft max output for the class prediction. And over here we have the Lenet.h, which includes all the macros. As you can see, we have used the define keyword here, and after which we have the test.cpp, which includes the test bench for our program. And this is the results that we have obtained. So we have successfully passed the simulation of our project, and we have performed synthesis, and this is the resource utilization that we have obtained. So as you can see, we have 35 BRAMs, there are 10 DSP slices, and there are 2,635 flip-flops, and we have 4,826 LUTs. So this consists of, so overall, this consists of 50% of 50 to 51% of DSP slices, 4% of flip-flops, and 45% of LUTs. So we have noted this down in the pie chart below. And yeah, so we have successfully implemented and debugged the Lenet 5, and we have used Vitis HLS and to run our code, and we have tested convolutional pooling and fully connected layers in a modular design. And for a future scope, we could probably use larger data sets, and more random weights and samples can be added. Thank you.